Hello students, this is me Ghulam Mustafa. Today we will discuss the fourth chapter of the same book Robin J. Wilson, Trees. In our mind there is a question arising about the trees, why we are studying the trees, and who gave the concept of trees and why. So let's begin with the historical background of the trees. Two mathematicians, one is the Kirchhoff, developed the theory of trees in 1847 in order to solve the system of simultaneous linear equations. Also, trees helps to solve the electric network problems. Another mathematician, Cayley, in 1857 discovered important class of graph called trees, considering the change of variable in the differential equation. Also, he made a relationship of trees with the differential equation. So let's understand what is tree. A tree is a connected, a cyclic graph. A graph is acyclic if it has no cycle. And another term used in a tree, that is forest. What is forest? A forest is a graph that contains no cycle. It means that cycleless graph is known as a forest. Or a forest is a tree if it is connected, or components of forest is called tree, and forest is simple graph. So these are examples of the graph. This is a tree with 2 points, and this is a tree with 4 points, and this is a tree with 5 points. We have some assumptions about the tree in the form of note I have written over there. One is that every edge of a tree is called bridge. It means that when we want to connect two edges, that edge is known as a bridge. And another one is every vertex of a G or tree which is not end vertex is necessarily a cut vertex. It means that if we have a graph, then it is not sufficient that each vertex should be a cut vertex. If a graph having two vertex, then end vertices are known as a cut vertices. We have a theorem which makes more easy to understand some terms of this graph. This is a theorem. If the graph G has n vertices and m edges, then following statements are equivalent. One is G is a tree. There is exactly one path between any two vertices in G, and G has no loop. And third one is G is a connected, and the number of edges should be less than the number of vertices, and G is a circuitless, and similarly the number of edges should be less than the number of vertices. And G is a circuitless. If we add any new edge to G, then we will get one and only one circuit. So let's prove the first statement. G is a tree. Here, if G is a tree, then the second statement implies to the first, or first implies to the second. Because of that, if a graph is a tree, then it should be connected according to the definition of the tree. So first implies to 2. If G is a tree, then it is connected and circuitless. Thus there are no loops in G. There exists a path between any two vertices of G. And second statement is that there is exactly one path between any two vertices in G, and G has a no loop. It implies to the third statement. Third statement is G is connected, and m are edges and n are vertices. It means that vertices are less than to the edges. So G is a connected. We use induction method, or mathematical induction is a technique to prove or true any statement. So similarly here we use that technique to prove or true, to make a true to this statement. We start from 0 or 1. There is a no matter. So where you want to start, it is not sufficient or necessary that we should have to start from the 1, and we will prove. So let's begin with the induction basis step. First step is known as a basis step. I have taken m is equal to 0 if G is a trivial and statement is obvious true. And induction hypothesis second statement, if m is equal to n minus 1, when number of edges less than L, where L is a greater than or equal to 0, and L is any number which is which belongs to n natural number. So n you can take in any number. And third statement is induction statement. M is n minus 1 when m is equal to L plus 1. Because of that, I have make a relationship m is equal to n minus L, and m should be less than or equal to L. So just you have to substitute here. And I have make a supposition for edge EB and edge NG. Then if I eliminate, or if I subtract the one edge from the same graph G has L edge, and then if I subtract G minus E, then it will becomes L edge. If G minus E is a connected, and G minus E has two components G1 and G2, and then there be N1 and M1 edges in G1, similarly N2 vertices and M2 edges in G2. Then make a relationship with the N vertices, and M edges will become N is N1 vertices and M2 edge. Similarly, M having a M1 edge plus M2 edge plus 1 edge, 1 vertices. By using induction hypothesis, I have taken N is equal to N1 vertices and M2 edges. Similarly, I have make a relationship with M edge with the N1 plus M2 plus 1 vertex. Because of that, if there is a one edge less than the number, one vertex less than the number of edge, then in this situation it will becomes greater than. Therefore, I have written over here the one edge is greater is compared to the number of edge. By induction hypothesis, as you know that from here m is equal to n minus 1, so I have written over there m1 is equal to n1 minus 1, and similarly for m2 n2 minus 1. So then m should be, the number of edges should be n1 plus n2 and less than 1 it should be. So this whole statement is equal to n minus 1. Other proofs you can do by using induction method, and by taking the reference of these three statements that I have proved, you can prove it.